Okay, so now we're going to look at another example of a second order system. Here we can have potential stored in our inductor, L, and our capacitor, C. And we're going to measure the voltage drop across our capacitor compared with the input voltage at E of S. And so again, if you want to try to have some practice with transfer function, this would be a good place to stop, and then on your own try to find this transfer function here. Okay, so now you're back, and I really wonder if anyone's actually doing this, but I'll give that opportunity and let you know when there's some work you can do on your own. But one way that we can do this, and again, with circuits, there's going to be multiple correct ways to solve it. We can say that the impedance across the capacitor over the total impedance of our system is going to be representation of the voltage out over the voltage in. So 1 over CS is the voltage across capacitor. Ls plus R plus 1 over CS is the voltage across the whole system. Because they're all in series, we can add up all of those impedances individually. And if we want to have these by voltage drop, we could multiply them also by the current of our system. I'm just skipping that step. But either way, our final transfer function, let's make that prettier, final transfer function should be 1 over LCS squared plus RCS plus 1. And if we want to have this in standard second order format, we will need to divide by that LC. So we can say that this voltage C of S over E of S is equal to 1 over LC divided by S squared plus R over L, because those C's cancel out, S, plus 1 over LC. Now, for this, we can go through, look at our system, and say that A, if we want to have it in standard second order system, where we say this is equal to A omega n squared plus S squared plus 2 zeta omega n S plus omega n squared, we can see that omega n squared is equal to 1 over LC, which means that our natural frequency, omega n, is equal to the square root of 1 over LC. And our A is going to just be equal to 1, because we can see that we have this 1 over LC in this position as well as in the position up here. So we have A is equal to 1, and we can say 2 zeta omega n is equal to R over L. And we have that omega n is equal to the square root of 1 over LC, so we can go through, solve for zeta. I'm not going to do that with variables, but if we have numerical values, it's a lot easier. It's just a lot of algebra, which I don't feel like doing right now. But then we can solve for zeta with numbers. So for this system, we can now think about what would it be if we had a step function input. And again, step function, we go from 0 to a value, and that would be the equivalent of adding a switch and closing a switch or plugging in a battery. You get this little weird hybrid typewriter experience with the pencil that I just showed in front of the camera that doesn't exist, and having this writing, but hopefully it's a nice experience, and apologies if it is an irritating one. So here we have another second order system with a circuit, and we have a way that we can think of a step function being added, and I just want to do that because we talk about step functions a lot in this class, and we want to make sure that we understand what the real engineering aspect of that is. Okay, so that's it for this section of the video. Now on to the mass spring damper system.